Hello everyone, welcome to the lecture number 42 of this NPTEL lecture series on charging infrastructure, and today we will talk about another isolated DC converter, which is dual active bridge converter. Now if we recall our previous discussions, we were discussing about the full bridge isolated DC converter in detail, where we have seen that the circuit will look something like this. It comprises of two half bridges called as the leading leg and the lagging leg. And the lagging leg, and because of this particular structure we have seen different schemes of that full bridge converter. Then we move to do furthermore detailed discussion on the PSFB, which is a phase shift full bridge converter, which is nothing but a full bridge converter operated with a phase shift in between the turning off of the diagonal switches. Then for that phase shifted full bridge converter in detail, we have seen different operating modes. We have derived different conditions where we can achieve zero voltage turn on of the leading leg as well as the lagging leg, and that is when we can achieve a very less switching loss during the turning on instances, and at the same time we will get the control DVDT at the output of this half bridges, which actually improves the EMI performance of this converter. Then we have moved our focus on small signal modeling of this phase shifted full bridge converter, and with the small signal of phase shift full bridge converter we have also seen how we can do the closed loop control of this phase shift full bridge converter, and with the control objective of regulating the output voltage at a desired value. One can also introduce another control scheme like peak current mode control, where one can sense the transformer primary transformer current and then make sure the peak current of this transformer in the positive side as well as in the negative side is the same. That is when it will help in avoiding the flux working of this transformer, because if the flux in the transformer does not reset to its initial value, then it keeps on having some DC offset, and that offset will keeps on growing either in a positive direction or in negative direction, and which lead to the saturation of this transformer. And this DC offset may arises due to the non-ideality in the devices, like different RDS on, thus the voltage drop across these devices will be different. Also sometimes due to the delay introduced in the gate driver circuit, the average voltage which will be applied will be different, and that is when we will have the different voltage applied along the transformer. When the diagonal switches is on, they are not equal and opposite, and that is when it led to some DC residual flux which keeps on growing during the operation of the converter. So that also has to be addressed, and that one can address by using the peak current mode control by measuring the transformer primary current. So these were the things we have discussed in detail. We will now move ahead our discussion towards another isolated DCC converter called as a dual active bridge converter. But before starting that, let us also try to write down disadvantage of PSFB. Now this disadvantage includes the first thing, because of this diode rectifier at the secondary stage, there is no possibility of bidirectional power flow. So no bidirectional power flow that we can write. That is the thing, power can flow only in one direction from this side to this side. However, because of the presence of this secondary side diode bridge rectifier, we will not have any bidirectional power flow. Only the power flows from input to the output. Now the next thing is, we have already seen we have limited range of short switching, because we have also seen that for the leading leg it is not a problem. The leading leg switches will go for soft turn on. However, the lagging switches will require the circuit operation in such a manner that L leakage will have enormous amount of energy to discharge the C3 capacitor to 0 and C4 capacitor to V in. So we have limited range of short switching, especially in the light load conditions. The achieving the ZVS in the lagging leg is a quite a difficult task. Then third point what we have in this one is that we have large inductive filter at the secondary side, large inductive filter in the secondary side. That is again one of the concern. This is also takes good amount of area, it also impacts the power density of this isolated DCC converter. Then another point, we have already discussed, this is flux walking which will take place. However, this can be arrested by solved by peak current mode control. They will slightly change the duty ratio from its nominal value to either less or more, and that's when they can control the peak current of the transformer in the positive and negative side to the nominal values. That is also one disadvantage which one need to address. Now let us try to see how one can address this thing in DAB converter, which is again one of the very commonly used DC-DC converter, especially for high power application going up to 20 to 25 kilowatt power range. So let us try to see our dual active bridge. Now as the name suggests, dual active bridge, it is also called as the DAB in the short form, a very famous abbreviation as the dual active bridge, and one can then make this dual active bridge in the modular fashion and can obtain a very high power chargers by connecting them in series and parallel according to their requirement. So let us try to understand what is a DAB converter. Now if you look very carefully, dual active bridge, as the name suggests, it has a dual, that means two active bridges which are present in the converter. So let us try to draw the converter, this thing. I am taking a liberty to draw these generalized switches. So this switch, generic switch, is nothing but one can achieve using MOSFET with a body diode, or it could be achieved using IGBT with the freewheeling diode attached to it. So in both the ways one can achieve this generic switch which I am drawing over here. So this is the generic switch. So it is having one bridge. So let me define this as V in, as we named, and as our nomenclature says, S1, S2, S3, S4. Now this again from the point A, let us say defined as the A1, is actually we will then take the inductance and then the B1 from the other leg. This is this is the L. I am just writing L. This L could be achieved either using the leakage inductance of the transformer or by putting the additional inductance in series with the one of the winding, either primary winding or secondary winding. Now this is the primary side, let us define NP, and on the secondary winding is defined as NS, and on the other side also we have something similar to that. Let us say A2, B2. This particular thing, let us say if we have the capacitor, we can connect it to the load CRL, and we have here we can define S4, S5, S6, S7, S8. Now if you look very carefully, we do not have any inductor kept at the output of the bridge. This inductor, we can assume that this inductor is being incorporated in the inductance L. However, that inductance value of inductance L, that we will understand when we will see the operation of this converter, how it works, and we can put the C and RL. So here if we assume that we have a good amount of C with the less voltage ripple, so we can also draw this converter to be something like V in, my S1, and we can just draw voltage source with V0 if we assume the C is sufficiently higher enough to keep the voltage at a constant value V0 or with a very small ripple. Now if you look very carefully in this converter, we have S1, S2, S3, S4, S5, S6, S7, S8. Now if you look very carefully this particular converter, this is dual active bridge because we have one active bridge from one side of the transformer winding and another active bridge from the another side of the transformer winding, and these two bridges are actually the active bridges. The reason being both the bridges can apply any value of voltages between 0 and V in from A1 B1 and and any value between 0 and V0 from A2 B2. In between that they can apply voltages obviously in a switching average sense. Now in this particular structure we can represent this transformer in the form of T model. So we can make this transformer NP NS to be looking like something like this, where this is the L leakage on the primary side, L leakage on the secondary side, and we have this magnetizing component of inductance Lm. If we assume if Lp comma Ls, the leakage of primary and secondary are small and less than, you can say that, L value, and if Lm is large enough or is large. Now this transformer we can define in this manner considering we have T model of the transformer. Now if you look very carefully, when this particular system, we can here we can apply any voltage between 0 and V in from A1 B1 and any voltage between 0 to V0 from A2 B2, obviously in a switching average sense. So since A2 B2 we can apply any value between 0 and V0, so we have to then take the A2 B2 voltage referred to the primary side, and that is when we can then define the equivalent circuit. We are applying any voltage from A1 B1, and this VA1 V1 is in the switching average sense. That means average voltage applied from the VA1 B1 in the switching period. So in a switching average sense, and we are now applying a voltage across L, and this voltage is nothing but again applied from the other side, which is VA2 B2, and this has to be referred to the primary side, so we can then write by N. So we can write in this way. Now again this is in the switching average sense. So thus what we can say that we are now, by changing any value from A1 VA1 B1 and any value from VA2 B2, we can then allow the current to either flow in this direction or flow in other direction. Obviously in a switching average sense we are defining that power flow to go from either from VA1 B1 to A2 B2 or from VA2 B2 to VA1 B1, and that is how we can able to achieve the power flow to go from VA1 B1 to VA2 B2 or from VA2 B2 to VA1 B1. Now if you look very carefully, our this circuit what we have drawn, let us take that circuit. Now, if you look very carefully in this circuit, now here we can do several, we can control this voltage applied from A1 B1 by actually changing the phase shift between, half bridge comprises of S1 S2 and half bridge comprises of S3 S4. So let us define this angle to be theta 1, that we can control the phase shift of turning off of the diagonal switches, as we discuss in case of phase shifted full bridge converter. Similarly, from the other side, we can also control the voltage applied from A to B2 by giving the phase shifted between the diagonal switches in the full bridges comprises of two half bridges S5 S6 and S7 S8, and that phase shift we can give it to be the theta 2. And along with that, we can also control the average voltage applied from A1 B1 or from A2 B2 by giving the phase shift between this both the full bridges by a phase angle, delta. So if we see, we have three control variable. We have delta, we have theta 1, we have theta 2. So delta is actually doing the phase shift between the two full bridges. One full bridge comprises of S1 S2 S3 S4, and another one comprises of S5 S6 S7 S8. The another phase shift is between the two half bridges in the full bridge 1. Let me say this is full bridge 1, and let me define this is full bridge 2. So theta 1 is the actually the phase shift given in the half bridges of the full bridge 1, while there is another possibility to provide the phase shift between the half bridges of the full bridge 2. So with these three phase shifts, we can achieve different kinds of modulations schemes we can achieve. By giving the delta, we are actually changing the phase shifted of the voltages applied from VA1 B1 and voltages applied from VA2 B2. While giving the theta 1, we are actually changing the duty ratio of the voltage applied from the A1 B1, that means for how much time we are applying plus V in voltage, and for how much time we are applying the minus V in voltage from A1 B1. Similarly, by theta 2, we are actually changing the duty ratio of the voltages applied from A to B2. You know that why duty ratio means for how much time we are applying positive V naught in one switching period. Similarly, this theta 1 is actually impacts the duty ratio of the voltage applied from the A1 B1, that means the time for which we are applying plus V in one switching period. So by doing this thing, we have different kinds of modulations are possible, and the moment we control the voltage of A1 B1 and A2 B2, we can either control the magnitude of the voltages applied from A1 B1 A2 B2, or we can provide the phase shifted between the A1 B1 and A2 B2. In both the cases, we can control the power flow from going from A1 B1 to A2 B2 or from A2 B2 to A1 B1. So that is why there are so many modulations are possible in these dual active bridges. So let us define different modulations possible, different types of modulation. Now the first type of modulation is called, we can also call it as a single phase shift modulation, which is also called as a short form as SPS modulation. Now in this, only one phase shift will be changed. Mostly it will be delta, which is being changed, and that's when by controlling this delta value, one can control the power flow going from one side, going from A1 B1 to A2 B2 or from A2 B2 to A1 B1. Now second modulation, dual phase shift. And dual phase shift modulation, also called the DPS, there are either along with delta, you can either do with change, you can also change the theta, or along with delta you can change the theta 2, or one can also do theta 1 comma theta 2. Again, it depends upon the designer who is designing that what kind of modulation they wanted to implement in their controlling scheme. Then the third one is, comprises of, since we have three modulation scheme present, so they can also say that triple phase shift modulation also called as a TPS modulation. Here we are changing all the delta theta 1 and theta 2, and that's when we can control the output voltage, or you can say that control the power flow going from A1 B1 to A2 B2, or from A2 B2 to A1 B1. We can do the power flow control using that by changing all the three delta theta 1 and theta 2 phase shifts. And however, here if we see when we discuss one of the modulation, simplest modulations, SPS modulation, you will see the current waveform changes by introducing this, delta theta 1 theta 2, and that's when one can achieve the lesser RMS value of the currents and in the circuit, and that's when the conduction loss in the circuit can be reduced. Now another kind of modulation is also possible, is, along with this, if you look very carefully in this circuit, the power flow can be either from A1 B1 to A2 B2, or from A2 B2 to A1 B1 by either giving the phase shift between these two voltages, or by changing the magnitude of voltage which is coming on these two sides. Along with that, we can also change the impedance offered by this inductance, and that impedance is nothing but, we can say, omega L, and that omega in this particular circuit, omega is nothing by 2 pi FSW, because we are applying the square pulses from A1 B1 and from A2 B2. So now this omega what we are writing over here, this particular omega, we can also change that particular frequency FSW, and that's when we are changing this impedance omega L, and that's when we can control the amount of current which is flowing from one voltage source to another voltage source, or from second voltage source to first voltage source. So another possibility is also could be, we can have triple phase shift with variable frequency, sometimes also called as the TPS VF modulation scheme, variable frequency, TPS VF, which is also called the triple phase shift with variable frequency. Similarly, one can also achieve dual phase shift with variable frequency, and I mean, again, this is very rarely used, but one can also use this as well. Very rarely used. Now if you see in this triple phase shift with frequency control, one can do delta theta 1 theta 2 and switching frequency FSW. One can write delta theta 1 theta 2 and FSW. Here either of these three, delta theta 2 or delta theta 1 or theta 1 theta 2, along with this we will have FSW here, FSW here, FSW here. However, it's very rarely used, because we get, as per several researchers who have worked upon, we can get very less RMS value of the currents flowing in the circuit, very less in this particular case. That's why people go for this particular approach. So what we saw, different kinds of modulation, where we have single phase shift, where we are just changing the phase shift angle between the full bridge 1 and full bridge 2. Dual phase shift, where along with this delta, that means the phase shift between full bridge 2 and full bridge 1 and full bridge 2, we are actually giving the phase shift either from the full bridge 1 or full bridge 2. That's when we can control the time period for which the V in voltage is applied from A1 B1, and the time period for which the positive V naught voltage is applied from A2 B2. That's when controlling the average magnitude of voltage applied from the A1 B1 or from A2 B2 by giving either theta 1 and theta 2 phase shift. And then finally we can also combine all the three phase shift and delta theta 1 and theta 2. That's when we can get the triple phase shift modulation, and we can introduce, along with triple phase shift, we can also introduce the variable frequency operation. Further, in all these modulations, since the phase shifts are given, all the switches are turned on for half the switching cycle period and turned off for half the switching cycle period. Only the phase shifts in turning on, or in other words turning off instances of the corresponding diagonal switches are given. Since the switches are on and off for half of the switching cycle period, so the phase shift given in between turning on instances will be the same as saying phase shift is given in between turning off instances of the diagonal switches. Now let us see the single phase shift modulation for developing the understanding about how this converter works in. So let me define the single phase shift modulation. Now in this, if we see, let us try to draw the waveform, because from that we will understand our circuit, from that we will understand our system. So if we see our first, let us first assume that S1 and S4 are turned on at the same time and turn off at the same time. S2 and S3 are turned on and turn off at the same time. S5 and S8 turn on and turn off at the same time. S6 and S7 turn on and turn off at the same time. So assume the first, it is S1 and S4, it is on. So we are having S1 and S4 which is on. Let me quickly draw the circuit for our understanding. We have S1, S2, S1, S2, S3, S4. Now, so my S1 and S4 are on at the same time. So let me draw S1 and S2 are on for the same time. Let us take, it is on for Ts by 2 period, and slightly take us more, and then it is off for another Ts by 2 period. This term up till this point is Ts duration, and this thing to this thing, it is Ts by 2. From here to here it is Ts by 2. Now the other switches, if we see, let us see S1 and S4 are on, and immediately after that my S2 and S3 is on. Then let us also draw my S5, S8, and let us also draw my S6, S7, and we let us also draw after that we A1, B1, we A2, B2, and finally at last we will draw our this, the current IL current which is flowing through the L, so which is IL. Now let us try to draw S2, S3, so it is 0, and then it is turned on for Ts by 2 period, and again it is 0. And if we see our S5, S8, let us, this, there is a phase shift which is given between S1 and S5, which is delta. Here the phase shift means the angle with which the turning on instances of S5, S8 switches are displaced or shifted. Now let us define an analogy. If there is an angle of 360 degree, it indicates that we have the time period nothing but corresponds to Ts, and that means if there is a phase shift or if there is a phase of 180 degree, then that indicates the time period of Ts by 2. Similarly, we can say that then giving phase shift of delta means we have time delay of delta by 180 degree into Ts by 2. That means if we give a phase shift of delta, then it indicates that we have time delay of delta by 180 degree Ts by 2. And thus we can define a term delta star, which is nothing but equal to delta by 180 degree, a kind of, we can say, which is a phase angle ratio, and this we have done it for our easiness. So we can say that if there is a phase shift of delta, then the time delay corresponding to that is delta star Ts by 2. So let us give one phase shift, which is, let us take at this point. Down and again it goes up. And this period, is, let us define this period going from this and this will be nothing but delta star Ts by 2, and then this period will be nothing but 1 minus delta star Ts by 2 period. Similarly, we can also draw S6 x7, because this since whatever the delta angle between S1 and S5, same delta angle will be there between S3 and S7. So S7 and S6 will be having the same phase shift as that of this. So if we take, our this thing, at this point, my S6 S7 is on, and it will turn off at this point, and here it was on, and then it goes 0, then it becomes 0 like this. Similarly this is also same as delta star Ts by 2, and this one is again nothing but 1 minus delta star Ts by 2 period. Now let us try to draw this VA1 B1, how it looks like. Since between 0 to delta star Ts by 2, my S1 and S4 is on, so this V in, since my S1 and S4 is on, I am applying V in voltage from VA1 B1. Then at Ts by 2 period, S1 S4 is turned off, and S2 and S3 is turned on. That is when I am now applying minus V in, because now S2 and S3 is on, so that's when A1 B1 is now applying the 0 or minus V in voltage from there, and then again it goes to V in. Similarly, in case of A2 B2, if we see my S6 and S7 is on, again this particular thing we will now write here one important thing, that means it is referred to primary side, so that we can then draw our IL current referred to primary side. So this is A2 B2, we can say VA2 B2 primary is VA2 B2 referred to primary side. Now if we look very carefully, the A2 B2 is, when my S6 and S7 is on, I am now applying from the secondary side minus V0, and this minus V0, if it referred to the primary side, it is nothing but V0 by N, where N is nothing but Ns by Np. So what we will get is, here we are now S6 S7, so here we are now applying minus V0 by N voltage from A2 B2 referred to primary side. and then after this my S5 and S8 is on. So now I am now applying V naught by N, and then again it goes to minus V naught by N from A to B2 refer to primary side. Now if you recall our phase shift full bridge configuration, here we are directly going from V in to minus V in, because we are now turning off our diagonal switches S1 and S4 at the same time. If we could have introduced the phase shift between S1, turning off of S1 and S4, then we could have introduced, you know, V in, I mean 0 state as well, and that's when our VA1 B1 will, instead of looking like going from V in to minus V in, it will look something like it goes from 0 V in, then to 0, then minus V in, and then to 0. V in 0 minus V in. That is when, if we are applying theta 1 phase shift, delta 1 phase shift, sorry, theta 1 phase shift, if we introduce in the half bridges of S1, S2 and S3, S4, that means we now turning off my S1 and S4's diagonal switches at different times, or you can say with the staggered turn off of S1 and S4 switches, we could achieve this kind of waveform, and that will actually reduce the average voltage which in a switching period, which will be applied from VA1 B1, average value of voltage. Now let us see how my IL current will vary. You know, here we are applying V in and V naught. So across this L, from here we are applying V in voltage, and from here we are applying minus V naught by N voltage. So that's when my IL current will actually rise with very fast slope, because the slope is nothing but V in plus V naught by N by L. With that slope it will rise. Then between this point to this point, we are now applying V in from this side and V naught by N from this side of this L. So our slope is now is reduced, and that is nothing but, we can say it is V in minus V naught by N by L. With that slope it is rising. Similarly, in this instance, we are applying minus V in, on the other side we are applying minus V naught by N. So we are now having a very sharp slope which will actually be looking like this. So sharp negative slope we have, which goes like this. From, in this case it was, we are applying minus V in plus or minus V naught by N by L slope, and this one, and from here to here we are applying minus V in from one side, on the other side we are applying minus V naught by N. That's when my slope is nothing but minus V in plus V naught by N by L. Here the slope is drawn in this way, which means that we have taken a condition where our V in is greater than V naught by N. That's why I have a negative slope, but this negative slope value is reduced. This waveform is for this case, and now this is, let's define this as this. If we say this is I naught, and which is same as this one, if we take here, so we can then draw curve like this, you know, for better understanding. And this is, let us define this as I naught, this value to be I1, this value to be I2, value to be I2, this value which is going over here is nothing but I3, and this value we can define I4, which is equal to I naught, which is also equal to I4. Here, in order to ensure the flux does not have some offset, we must ensure that I2 should be equal to minus I naught and I1 should be equal to minus I3 and I4 should be equal to I naught. That we must ensure this condition. In order to ensure this, ensures no offset in the transformer primary current, or in better word, no DC offset in the transformer primary current, because if there is a DC offset, then the flux in the transformer will keeps on going in one direction and it will get saturated. So this is the very simplest waveform we have drawn by giving just the phase shift between the full bridge 1 and between full bridge 2, the switches in the full bridge 1 and full bridge 2. And here we assume that both the switches are turned off at the same instances. There is no phase shift introduced in the turning off of the diagonal switches in the full bridges. So this is the simplest single phase shift modulation waveform. We will derive the conditions, considering this, how we can design this L value and how the current waveforms look like for different magnitude of V in and V naught voltages. Those things we will see in the next class, and with that we will then look into some of the important aspect of this DAV converter. Thank you very much for patiently listening to this lecture. We will meet in the next lecture. Till then, thank you.